Now, when we talk about simple harmonic motion, one of the important quantities that's conserved in that motion is going to be energy, and that forms an entire section of this chapter, 11.3, energy in simple harmonic motion. And you're already familiar with all the aspects of energy that we're going to experience with a spring mass system. That handwriting just looks terrible, but we're going to go with it. Remember, we're looking at a simple system where we have a wall, a backstop, a perfectly frictionless, perfect surface, some mass like this attached to a spring, oscillating about some central point, some central fixed point. So it's going back and forth. As this thing is moving, you have a mass in motion. It's going to have kinetic energy of 1/2 mv squared at any given instant in time. Now that velocity, and remember this is all motion in the x directions. I was going to say, well, anyway, you have 1/2 mv squared. That velocity is going to be moving to the left and to the right at times. When you're at the maximum points of displacement, that velocity is going to be 0. So the kinetic energy is going to oscillate back and forth. But you also have this potential energy, and I write U sub EL for elastic, and that's 1/2 kx squared, where k is a spring constant for that spring. I mean, and the reason we had that was, you know, we had this restoring force, F sub spring equals minus kx. Same k is used there. This looks a little bit confusing because I realize that I'm using k over and over, but I have like a little k for the spring constant right here, and this is kinetic energy. So it's probably worth labeling these. That little k is my spring constant. The total energy at any given time, you'll remember, the total mechanical energy is going to be the kinetic energy plus the potential energy, and this is conserved. It's another throwback to 131, and so what we're going to say is that E equals 1/2 mv squared plus 1/2 kx squared is a constant. It's the same thing when I say that it's a constant as when I say that it's conserved. This thing will move back and forth in our perfect little system forever and for all time. What's interesting is, if you look at this system one more time, as though this is going to be the last time we look at it, which it's definitely not, you'll notice that the energy at maximum elongation is going to occur when x is equal to a, or x equals minus a. But energy at max elongation is equals 1/2 mv squared plus 1/2 kx squared. Here, the velocity is going to be 0. When it reaches the farthest point out, it comes to rest briefly, and then the mass starts to slide back towards the center, and x is going to be equal to a at that point. So the point being made here, and the important thing about all this, is that the energy of this system is going to be 1/2 ka squared, where a is the maximum amplitude of that motion. So when I was writing on the last page that energy was a constant and it was a sum of these two terms, well, I'm going to write it one more time: 1/2 mv sub x squared plus 1/2 k x squared equals 1/2 ka squared. So if I looked at this motion and I knew the mass and I knew the spring constant, if I look at that maximum elongation, that a, it allows me through this equation to have two unknowns, or two variables, v sub x and x, so that at any other x value that I could determine, like, you know, x equals 0 or x equals half of that maximum amplitude, I can plug that value in there and I can solve for the velocity. If I isolate that v sub x term in this equation, what I end up with, and it's worth doing this on your own, I'm just going to draw out the answer Remember, I have a Vx squared, so I'm going to take a square root at some point, giving me the option of this plus and minus. But what it leaves me with is this. V sub x equals plus or minus the square root of 2 over m, and then that k a squared over 2 term minus k x squared over 2 like that. Or canceling out these two values, I'm going to write it right here, and I'm going to try and write this neatly. Sort of wrote myself into a little corner. But notice I have k terms in each one of those interior terms. So I'm going to have k over m. The 2's cancel out, and I'm left with a squared minus x squared. Just a useful expression if I want to find out the velocity of that mass as it's going back and forth. Notice when x equals 0, this x term would be 0, and I would have plus or minus some fixed quantity. And the plus or minus would depend on what part of that cycle it was on. If it had come from the right, well, you would use a negative sign. The object would have a negative velocity. It'd be heading left. But if it had already compressed the spring and was bouncing back towards the right, well, you'd use a positive sign for that v. You'll also notice from this, I just said, if x equals 0, you're going to end up with some maximum value for the velocity. So if you knew k and m and you set a, you would know how fast, the speed of this mass at x equals 0. And that would just be v sub x equals the square root of k over m times a, like that. So this is going to be, oh, and sorry, I meant to write v sub a sub max for that quantity. These little expressions, you're going to want to have these not memorized, but you're going to want to know where they are because you are going to use them at different times when solving certain problems. So this is the end of that section talking about the energy contained in that simple harmonic motion of this mass spring system.